In our previous session, we talked about exponential function. Today we are talking about logarithm. Logarithm is the inverse operation of exponential function. In mathematics, we always have an inverse operation. We have multiplication as inverse operation of division, or subtraction is inverse operation of addition. And therefore, the logarithm is undo of exponential. So it's opposite or inverse operation of exponential. For instance, in exponential function, we have a squaring a number, right? So we have logarithm, which is finding the square root of something. So in exponential function, we have y equals to b to the x power, right? This is exponential function. While in logarithm, we have log, that is a symbol of logarithm, and we have a base as b, same as b we have here, and we have y as exponent, which is equal to x. So log base b of y equals, this is a relationship that we are talking about in logarithm. In fact, in logarithm, we ask about a square root of a number. When we have a number, we ask ourselves what number multiplied by itself that gives us this number. So the way we ask question is, how many of one number do we multiply to get another number? Whatever the number is, that is logarithm. Let's say we have an exponent which is 2 to the third power, right? It means 2 times 2 times 2. This is an exponent. In logarithm, we ask how many 2's do we multiply to get 8? 2 times 2 is 4 times 2 is 8, right? So we ask how many 2's do we multiply to get 8? So the logarithm is 3. We write it as log 2 of 8 equals to 3. So this is the same as the exponent that we have here. It means we have 3 2 multiplied together give us 8. Or let's say we have 5 to the third power, right? It means 5 times 5 times 5. 5 times 5 is 25, and times 5 is 125. So this is our exponent, and this is base. In this section, we write it as log base 5 of 125 equals to 3. So this is our base. Log base 5 of 125 is 3. It shows that 5 multiplied 3 times by itself and gives us 125. The standard form of writing logarithm is log base b of y equals to x. The same as exponent. In exponent, we would write b to the x power equals to y, or y equals to b to the x power, right? This was our number, this was exponent, and this was result. The same is here, except the reverse operation. We are asking how many times b is multiplied by itself give us y. So this one is in fact exponent, but we are calculating for this one, saying how many times b is multiplied by itself and give us y. Or let's say log 5 of 25 equals to 2. In fact, we are saying 5 is times to itself twice and gives us 25. So the way we are asking question is, how many of one number do we multiply to get another number? Let's say we are asked to calculate log 5 625. That means how many times 5 is needed to be multiplied together to get us to 625. Then the answer is 4. And if you write it this way and say 5 to the 4th power and calculate that one, 5 times 5 times 5 times 5, you see the result is 625. So the log is saying how many times, in fact, 5 is multiplied by itself that give us 624. Log 5 of 625 equals to 4. Another example could be, for instance, log base 10 of 100 equals to what number? We know 10 times 10 or 10 squared is 100. So we can write as 2. And this is our x. So an exponent of 2 is needed to make 10 into 100. What if we are asked to calculate log base 3 of 81? Then we know that we need 4 of these 3 multiplied together give us 81. So x equals to 4. If you recall our discussion on perfect square, you can answer the logarithm question easily. If you remember, we had perfect square and we found the square root for perfect square. Remember, the square root for perfect square where we had radical 1 equals to 1, since 1 to second power equals to 1. Then we had radical 4 equals to 2, since 2 to the second power equals to 4. We had radical 9, which was the roots for that, the square root was 3, because 3 to the second power was 9. Then we had 16. The square root for that was 4. 4 to the second power, or 4 squared, was 16. Let me write the rest of that here. So a square root for 5 was 5. Square root for 36 was 6. Square root for 49 was 7. Square root for 64 was 8. Square root for 81 was 9. And square root for 100 was 10. So knowing these square roots, perfect squares, will help you in finding the answer for logarithm questions that is raised for you. So let's do some practice on logarithm. Let's say, let me clear this board first. Now, let's say we have log base 7 of 49. It equals to, we know that 7 is perfect square, and the result is 7 times 7 is 2, where x is 2. What if we have log base 7 of 1 over 49? Based on the properties of exponent, we know that whenever it's in denominator, when a number is in denominator, the exponent must be negative. So we have negative 2 as exponent or as x. So let's say we are asked to calculate the logarithm for 5 to the second power. Then we write as 1 over 25. The logarithm for that is log 5, 1 over 25 equals to minus 2. What if we have 10 to the second power? This is again a perfect square, and we know that logarithm for that is log base 10 of 100 equals to 2. And let's say now we have logarithm and we are asked to write it in exponential form. So we have log base 2 of 32. What is our x or exponent? We know that 2 must be times by itself 5 times and then give us 32. So 5. It means 2 times 2 times 2 times 2 times 2. It gives us 32. Or let's say we have log 6 of 1 over 36. We know 6 is perfect square in a denominator, so it must be minus 2. 6 times 6 is 36, but since it's in denominator, it's negative. So log 6 of 1 over 36 is minus 2. Let's say we have log 14 of 1 over 196. Again, this is a perfect square, but because it's in denominator, we know that it's going to be a negative exponent. So log 14 of 1 over 96 is minus 2. Log 14 of 196 is 2. Let's say we have log 8 of 64. We know the x or exponent for 8 to become 64 is 2. It's a perfect square. But if we had log 8 to 1 over 64, answer was minus 2 because it's a negative exponent. That's why it's in denominator. So I think you know now the logarithm. Let's talk about other concepts, which is common and natural logarithm and the properties of logarithm. So a logarithm can have any positive value as its base, but there are two bases that are very useful and we need to remember that. One is called common logarithm and the other one is natural logarithm. Sometimes you will see a logarithm is written without a base, like this, log 100. There is no base here. This usually means the base is 10. It is called common logarithm. Even there is a button on the calculator like this, and it's referring to common logarithm. It means that how many times you need to use 10 in a multiplication in order to get a desired number. Let's say we have log 1000 It means log 10 1000, that which is equals to 3. Whenever you see log x, you know that x equals to 10. So that is how we know that logarithm, if you see log 100, log 1000, you automatically know that that is common logarithm and the base is 10. So if you have something like log 10,000, you know that the answer to that is 4, because it means log 10 of 10,000 equals to x, which is 4. So this is common logarithm base 10, and you can see it very often in mathematical equations. And also we have natural logarithm base e. This is base 10 and this is base e. There's another base that is very common, and you can use it in your field, or you would see it in many mathematical area. That is base e, that is equivalent to approximately 271828. These are the first digits, first few digits of a long number that mathematicians use a lot, and on a calculator you see it as ln button. It means that how many times you need to use e in a multiplication in order to get a desired number. For instance, you have ln 7.389 equals to, I'm going to write it here, log e of 7.389 is not equal but approximately is 2. That actually means that e number, which is 2.71828, if multiplied by itself or squared, approximately gives us 7.389. So this is the exponential form, and this is the log for e number, or e base e. So these two, base 10 and base e, are two base that very often is used in mathematical field. Now let's talk about properties of logarithm. There are 4 basic properties of logarithm if the bases are the same. Sometimes they are called laws of log or logarithm. So the first one is like the same as we had in exponent, is product rule. It says if we have two things being multiplied together, we can break up the logarithm to 2 logs that is added together. If we want to use an example, it will be log 2 of 8 times 32 equals to what? We can write it as log 2 of 8 plus log 2 of 32. We know that log 2 of 8 has an exponent of 3, and log 2 of 32 has exponent of, this one has exponent of 8, right? So we can write it as, that gives us a log of 2 multiplied by itself 8 times give us 256. So this is our log. So the rule actually says if you have a product, the log can be turned into addition outside the log, and vice versa. The log of a product is equal to the sum of the logs of the factors, as we can see it in this example. Let's go to the second rule. So the second rule is quotient rule. In the previous rule, the multiplication became addition, right? Likewise, if you have a division, it becomes a subtraction. The rule says if you have a division, you can turn it to a subtraction. So you can write it in separate statement. So the law says that log b of m over n can be written as log b of m minus log b of n. So any division can be turned to a subtraction and written in two different statements. For instance, we have log 7 of x over 4. We can write it as log 7 of x minus log 7 of 4. Or sometimes the numbers are very big and we use this kind of breaking it to the factors, so it's easy to handle it. For instance, let's say we have let me make some room here. We have log 10 of 5 over 14. We can write it as log 10 of 5 minus log 10 of, you can break 14 to 2 and 7, right? So you can write it log 10 of 2 plus log 10 of 7, because these two are multiplication and this is the general format of quotient rule. We break the log, but because it's a big number, we can use the first rule, that is product rule here. When you break it into these pieces, then it's easy to calculate the logarithm. So the log of a quotient equals to difference of the logs. So let's say we have log 7 of 1.5. When you see that one, you have to figure out what is 1.5, right? So 1.5 actually has 3/2. So we can write it as log 7 of 3 minus log 7 of 2. This is a simplified one and we can solve for this logarithm. We only need to remember that a logarithm is the same as exponent. If you remember that, then you will be able to solve for logarithm. The third property of logarithm is power rule. The power rule says that the log of a power equals to the product of that power. Whenever we have a log and it is raised to a power, we can rewrite it by taking the exponent and move it to up front. Then we can solve for the log. Log 3 of x raised to the second power. We can bring this power to up front. So we'll have 2, that is the power log 3 of x. Or let's say we have log 12 of 5 raised to 11. So we'll have 11 in front of our log, and then we'll have log 12 of 5. So whenever we have a log and it's raised to a power, then we rewrite it and bring the exponent in front of the log. Fourth rule is inverse rule. The inverse rule says that log b of b to the x power equals to x. the inverse function undo the effect of the original function. This means that if you take the log of an exponent function with the same base, you get back to where you started. So, for instance, log 5 of 125 equals to log 5 to the third power equals to 3. In inverse rule, we are asked what power can you raise b to in order to get bx. Let's say we have b raised to what power we get b to the x. The answer is if you raise b to the x power, we get bx. So the answer must be x. That is why we write as log b of bx equals to x. Because the exponent here, log b to the x, represent the power that you raise b to in order to get x. That is why when you have log 3 of 27, you'll have 3. Or when you have log 2 to 32 equals to 5. It says that how many of these 2 you need to get 32? 5 of this. Then the answer to this one actually is the answer to whole log. By knowing the inverse rule, you'll be able to calculate any logarithm without needing a calculator. So let's say you have log 2 raised to the 16. So the answer is 4. You need 4 of these 2 in order to get to 16, right? So this is the answer to this section, the same as the answer to whole logarithm. Except these 4 rules, there are also other extended rules that we need to know. Extended rules of log. So we don't have a log with a negative base. So we don't have log minus b of x. No, we don't have such a things. Then the log of a negative number also do not exist. So we don't have no log of a negative number. So we don't have log b of x, right? The third one is we don't have the log of 0. So we don't have log b of 0. The log of 1 is 0. So if you have log b of 1, you know the answer is 0. We have log b of 1 equals to 0. And the fifth one is the log with base b and the number b is 1. So if you have log b with number b, that equals to log b of b equals to 1. So these are the extended rules of logarithm that we need to remember. We also have negative logarithm. We have negative logarithm, which means how many times to divide it by the number. Remember, logarithm is about multiplication, right? If it is negative, it means the opposite of multiplication, which is division. So you need to divide number n times when you have a negative log. For instance, if we are asked to evaluate log 2 of 0.5, we know that a half is 2 minus 1, right? So if we divide 1 by 2, we get half, right? So log 2 of 0.5 equals to minus 1. Or if we are asked to evaluate log 8 of 0.125, then we know that if we divide 1 by 8, then we get 0.125. So log 8 of 1.25 equals to minus 1. Now let's evaluate some log so we get the hang of it. Let's say we are asked to evaluate log 3 of 1 over 81. So we know that 81 is equal to 3 to the 4th, right? So if you write it in exponent form, you'll have 3 to the 4th power is equal to 81. But this one is 1 over 81. Based on the exponent rule, we know that whenever our exponent is negative, then we put it in denominator. So we'll have 1 over 81. Log 3 of 1 over 81 is minus 4. Let's say we are asked to evaluate log base 3 of x over 5. First thing we do is to write our formula, which is log base b of x over y equals to log b of x minus log b of y, right? So we can rewrite this one as log 3 of x minus log 5, log 3 of 5. Or let's say we are asked to evaluate log 8 of 2x. Whenever we have a log that is product, we can write the log, and instead of multiplication we can write the sum of them. So log b of mn, if we have log b of m, log b of n, right? So we can write this one as log 8 of 2 plus log 8 of x. Or let's say we have, let's be clear here first. Let's say we have log 4 of x over yz. Again, it's a quotient rule. We know the quotient rule says log b of m over n equals to b of m minus log b of n. So we can rewrite this one as log 4 of x minus log 4 of yz. But yz is the product. So the next step is to simplify this one. So we have log 4 of x minus log 4 of y plus log 4 of z. Because so we have the second formula as log b of m times n, which is log b of m plus log b of n. So let's clear this section first. And now the next one, we have log 5 of 5 radical x. Whenever we have a radical, we change it to exponent. So a square root, remember, a square root for radical x equals to x 1/2. So we rewrite it as log 5 of 5x to the 1/2, and then we start to simplify this one. The product rule applies to this one, so we'll have log 5 of 5 plus log 5 of x of 1/2. So let's recall our power rule, which says log b of x raised to y. We can write it as, we can bring y to the upfront, and then we'll have y log b of x. Now we can do the same here. We'll have log 5 of 5 plus 1/2 comes in front of the log, so we'll have 1/2 log 5 of x. Now let's do another one. Let's say we have log 2 of xy raised to 1/2 power. So this logarithm, the whole thing is raised to 1/2. So we need to do two separate operations on that. One is multiplication, the second is power rule. We start with 1/2, we bring it up front, 1/2 log 2 of xy. So we'll have 1/2, because this is the multiplication to whole thing, we put it into parentheses, and then we'll have log 2 of x plus log 2 of y. Now we can distribute this one to whole parentheses, and then we'll have 1/2 log 2 of x plus 1/2 multiplied to this one, to the second part, so we'll have 1/2 log b raised to y. Now this is the simplified form of log 2 of xy raised to 1/2. So I'm sure you are ready to do some practice at home. Let me put some logarithm here so you can practice your logarithm at home. Let's say we have simplify the following logarithm. So log base 5 of 5 raised to n power, log base 2 of x raised to second power, log base 2 of 8x raised to 1/3, log of 8x to third over 2y, log 2 of a squared minus b squared over ab. Solve for x in the following logs. Log base 5 of 180 minus log 5 base 5 of x equals to log 5 of 12. Let me write it neatly. So the next one is log base 3 of x to the second power plus log base 3 of 5 minus log base 3 of x equals to log base 3 of 50. One more problem, and that is log base 2 of 12 raised to the x power plus log base 2 of 3 equals to log base 2 of 36. To solve these problems, you only need to remember the rules of or the properties of logarithm. Next, we talk about a logarithmic function and how to graph it.